Okay. Well, I've been at DeepMind for almost 2 years, and I'd love to talk about the work that we are doing there, but I can't as yet. But I can tell you about the tools that come from open source that we are using. This one, Grisette, was developed by my student Siri Lu at UW, who will be graduating soon. And based on Armando's characterization this morning, this research is about 7 years dead. It's nothing neural in it. It all ended in 2017, if I remember. So perhaps it takes 7 years to be dead before it's useful. Let's take a positive spin on it. So some of you may know that I've been working on systems as one line of work that make it easier to use constraint solvers to do verification, synthesis, and other tools. Armando was the first one I convinced to build a sketch. Then when Amina Torlak was in my group, she built Rosette. And Grisette is, you could say, the third generation of sketch. And I'll get shortly to what challenges it's solving. But maybe to refresh what we are doing. So what is symbolic compilation? Symbolic compilation is the process of making it easier to write constraints of your system. You write it as a program that has not just normal concrete inputs, but symbolic inputs such as X in here and H for the whole in the synthesis program. You translate that into a formula, right? So set of constraints. And then you ask solver in one or multiple queries to answer various questions, such as is the system safe, and give me a program that satisfies certain properties, and so on and so on. Okay. And it's the symbolic compiler that is important. It's just that it's not just a piece of engineering. There are many things that it actually tries to address and do well, such as usability for people who write those programs, give them good diagnostics, good abstractions. And then the quality of the formulas is part of the algorithmics in the space, right? We want to have control over what these formulas are, okay? So part of what is challenging is making this compilation of the symbolic programs take care of multiple paths simultaneously, right? Because you could do it in multiple paths, the way you've seen it in symbolic execution, perhaps every path separately, as was done in testing. This doesn't quite work well. This path explosion will kill you, in particular, if the program encodes a program space. So in synthesis, you would typically write the grammar as a program with holes. And so you really need to put all the paths together into one formula to give it to the solver and ask, give me the values in the program and find the path, you could say, that corresponds to the desired program. So you need to do better than this. Well, we could do bounded model checking, which takes these paths together and merges them with something like an ITE. And that's okay, you don't get path explosion, but you are losing information about these constants here, which is extremely important to preserve and push through the program, because in a system like this, you want to do partial evaluations. So the constants need to be preserved so that you evaluate away a lot of the stuff. Without going into much details, why that partial evaluation is crucial, you need to preserve this constant. So this is where I'll get to it later. Okay, so what we contributed in Grisette was, well, it gives you a smaller formula and gives you about 3.7 speed up over state of the art of how formulas are created using a surprisingly small insight, which I'll show you. And this is where we really started. We wanted to build it as a functional library as opposed to a new kind of a compiler, a library that is easy to build. You get a recipe for porting it to other systems. That was the original goal. So reusable in that sense. There is a Haskell implementation as well. So how reusable are symbolic compilers today? Well, typically when you write a verification or synthesis symbolic system, you start by observing that, well, we need to compress that space somehow using a domain-specific language. Otherwise, if you write it in assembly or C++, it will be too large to reason about. So it's nice to have a DSL. You write the DSL interpreter, and you write it on top of some symbolic virtual machine, for example, Rosette. And that will essentially translate the DSL using first Futamura projection into constraint. So all you need to write the DSL in the symbolic language, okay? And so in that sense, it's reusable. You just write another DSL for another problem you have on top of that virtual machine, right? So that's good. It's reusable because all the reasoning, translation to formulas is done by the stuff underneath. And it's efficient because there are good ways of translating multiple paths into a single formula implemented there. So that's all good. What is not so good? What is not so good is that to build the language in which these DSLs are written, the approach so far has been to take the underlying language, such as Racket in this case, and in the case of Sketch, something like C, and make a subset of this language symbolic. So I say this construct can accept symbolic formulas, values, and those cannot. And that leads to a confusion as to what the semantics is. If you take a language defined over integers and now it's over symbolic integers, it leads to confusion sometimes, okay? It's also not easily portable because the algorithm for this compilation is sort of hard-baked into the Rosette interpreter or into a compiler. You cannot easily move it from Racket to, say, Java. And finally, to be efficient, it's functional, but not purely functional. So it relies on state to do optimizations. That's make it even harder to port and sometimes understand, okay? So what we wanted is to get a portable essentially recipe for building it. And portable in the sense that the symbolic value is not defined as part of this Racket++, but instead it is just a data structure that you pick up from the library, and it's truly nothing just as if you use the tree data structure, okay? So the underlying language is the same, it's just Haskell. And it is also safe, so you can now, thanks to type, know when you can use the libraries from the host language without passing bad things to them. That was pretty hard to do in previous systems, so you get that safety. And it also purely functional, so you can use functional program constructs like monad to implement stateful symbolic interpreters for things with coroutines by just using that data structure with monads in the well-known, understood way, okay? So the challenge is, how do you actually take efficient representation of multiple paths and put them into a library setting in a purely functional thing? Can you do it without losing efficiency? And in fact, if you do it naively, it all becomes 14x slower, okay? So the question really becomes, can we free ourselves from having to do it in a compiler, do it in a purely functional way, and actually not lose 14x, okay? So I'll talk about the efficiency, speed of compilation, how good the formulas are, what is the programmer experience now, okay? So first, let's talk about formulas, okay? And we expected to lose some performance. In fact, we ended up being better. And let me show you why this is so. It's a surprisingly simple insight. So here is an example of what a symbolic program. The red things are symbolic. So if statement, this is a symbolic condition. If this, then you get a list with one value symbolic in it. Otherwise, it's a list with two values. And then again, then you concatenate the lists. And then E should be the head of the list. And you'd like to understand what E is, even though this program is a mix of concrete and symbolic. So E will be either, x1 or x4. It will be either x1 or x2, right? Because you know that this is concatenated behind. And so you've seen that, okay? So the representation that has been used prior to this work, we call MEG for mutually exclusive guards. It was used by Rosette or by Koshik Sen's JavaScript system. Effectively, the value of D here, okay, which is that symbolic list, is this, if this is true, or it is a list where each element is an ITE condition, if that is true, and it is this list if this is true. And these conditions are mutually exclusive, okay? And as a result, okay, you can now apply this operation here on these things, right? These alternatives, so you can actually operate on these structures. Right? But as a result, 7 nodes were created even in this simple program. So we are creating extra nodes just to guarantee that these conditions are mutually exclusive. Turns out this is a large reason for the blow up of these formulas, okay? So what we do, instead of making these guards mutually exclusive, we say, okay, instead of doing ifs, let's do if else, so order them implicitly. And because they implicitly order, they don't need to be mutually exclusive, because this one you consult only if this one is false. So there is sort of mutual exclusiveness there, implicitly guaranteed by that order. So we call it ordered guards. And you see there are fewer conditions here as a result, because you don't need to make them mutually exclusive, okay? So what are the sources of duplications in these two things? Also, in MEG, you create sort of duplicate formulas, creating new nodes when you are making them mutually exclusive. In org, you create conditions when you reorder them, right? So if you start in this order, 4, 3, 2, 1, and you need to get it into this order, that reordering makes you create new nodes. So there isn't a free lunch. These two formulas are probably incomparable in theory. The important thing is, how does it work out in practice? And in practice, what is important is how you handle merges, right? So imagine that you have a representation of this symbolic value and that symbolic value, and it is this data structure and that data structure. You want to keep them in the same order so that you can then merge them symbolically as if it was just a merge sort, right? Walking through these lists. And then it is a linear merge, okay? And when you keep it as an invariant, okay, you can very easily merge them fast, and you don't need to reorder them again. Once you keep them in that ordered state, and formulas become reasonably small, okay? Then I will mention briefly one thing, that if you have long lists, of course, things are not very efficient, but you can use things like hierarchy, 1 and these 2, to create sort of nested structures to keep lists small, but maybe deeper, okay? That helps a lot. So how does it work? Okay, we evaluated several applications that were written for Grisette. We ported them, Rosette, ported them into Grisette. And what we see is that the compilation speed is faster, even if we implement it in the same system, faster over Rosette, but you could say Racket is slower than Haskell. And the speed of solving is also significantly faster, sort of between 2x and 5x, depending where you look, okay? That was surprising. But if you look at the reasons why, here are 4 points for 2 benchmarks, and you see that the reason probably for the speed is that the smaller the terms, this is the x-axis, the faster the solving speed. So there seems to be a correlation, perhaps not surprisingly, between the sizes of the formulas and solving speed. So it pays to keep those formulas simpler to get faster solving, okay? So I want to briefly talk about the programming interface, which is what we wanted to start with originally. Have something that is easier to understand, that the language that you then equip with symbolic things. How does it look like when the symbolic formula is just another data structure from your library? So I'll try to show a synthesizer on just 2 lines of code, very simple one, but hopefully this gives you a flavor. So this is the space of programs, so kind of a sketch. It's very simple. Essentially, it says the program will be x plus c, and you just need to synthesize the constant c. But I'll give you an example of what the entire space of programs is and how you define it. So these are example programs in that space. The specification will be an IO pair. So clearly C should be 3. This is the expected result. So first, you define your DSL syntax here. So this, you can see, this is just a grammar, but it is just the data type in Haskell, right? So it is symbolic expression. It's either a symbolic integer or it's an addition or multiplication, okay, which is recursive. The only thing that is different is that the children here are union M, a monad that includes this. The union M is this org container that contains the list in it, each with some symbolic condition. So you could say, well, your grammar could be a plus, which could be a plus under some condition, or multiplication under some other condition. It's an integer. That's the whole idea. So that's essentially the sketch of the space, the symbolic search space. And here is the semantics, right? Again, it looks like an interpreter. You will say, okay, when you have addition of x and y, it is interpretation of this plus y. But because X and Y are unions, you call the union version of the interpreter, which iterates over the things in this list. And you can easily build it by just lifting the interpreter from normal to the union thing with one extra call. So now we have a definition of the syntax and the semantics. And what this DSL interpreter does, it essentially interprets all possible abstract syntax trees that are in the symbolic list all at once, right? Because it walks over that symbolic data structure. And here, essentially, you define the program space. You can now evaluate it. You specify that when you evaluate it on input 2, it should be 5. Now you can print the result of the synthesis after you solved it, get the actual executable concrete programs all on one slide. And if you want, you can implement imperative programs or languages with just a state monad that is common, right? Except now you use the union to compose with the state monad, okay? And there are other benefits such as static types. You can be more careful about where things should be concrete versus symbolic, get huge speed ups for how fast the compilation happens. And perhaps interestingly, because the thing is purely functional, you can memorize the process of symbolic compilation. So if parts are translated again, you can just look up the results and plug them out, get them out from the cache. Parallelization also seems possible for the same result because things are purely functional. So one thing that is not in the talk is a synthesis library that we've been using to build some things at Google, some in open space. It uses Sanjit's algorithm on component synthesis, which seems to be still the best algorithm for symbolic synthesis with some extensions. So you can access that from this repo. And that's it. Hopefully finish ahead of schedule.
Are there questions? So let me maybe then start the discussion. Is like, maybe I didn't realize, how did you derive these rewrite rules that you use in Grisette? Were they automatically derived, or were they observed by what works best in the practice?
Which rewrite rules? The form of the symbolic value, the fact that we use. So there are rewrite rules in the sense that we simplify the Boolean formulas, but maybe what you are referring to is.
Yeah, exactly. Those are not rewrite. Those are not rewrite rules.
No, these are sort of, if you think of the program and see what would be the symbolic value of D, right? A is some list under some condition, some list under other condition. If you run the symbolic evaluation in this head, you will realize that D, this correctly describes the symbolic execution of the program.
Yes.
And this is how you would represent it, say, in Rosette or other systems that are careful about merging paths. And then how we realize that this is a better representation? Well,
yeah, that's the question. I thought that was actually maybe my misunderstanding. I thought that you had set of rewrite rules that you applied to get better representation.
I see. No, so we build it like this to begin with. When you start doing the execution, this is how you keep. This is, you could say, the structure of the formula that you keep inside. How we came up with it was Rosette performs this optimization of how it translates assertions to create really efficient formulas. Yeah. Clearly, it looks like you need to have a compiler in order to do it. It turns out that if you represent the formula this way, you get that assertion optimization essentially for free. That's how it came up to be. So
this was practically you checked into Rosette's optimizations and put it there in the.
And then I realized, oh, if I represent it this way, then we can get it for free.
Oh, I see.
And then it turned out to be useful not only to obtain that assertion translation in a good way for free, it also was useful throughout the system elsewhere because it replaced the mutually exclusive guards that have a lot of duplication with something more compact.
Okay.
So it was a little bit of a lucky move that was inspired by how can you get the efficient compilation of assertions that is not based on a compiler, but could be done as a data structure, where you can think of this as one format of the data structure. This is another format of the data structure.
Oh, I see. I see. I kind of picture in my head it's a set of rewrite rules, but thank you for clarification. Are there more questions?
So is there a formulation you can have of, like, I'm not sure exactly what is the quantity that is being minimized. I think like you're trying to maximize for speed and parallelism and other kind of byproducts, but is there like can you phrase this as a kind of as a Boolean function synthesis or something where you have a decision list or something?
I think what you want to minimize is the number of extra nodes that you create when you translate the program, right? If you look at this, right, C1 and C2 appears in the program only once each, right? But here they appear 1, 2, 3, 4 times, right? And yes, you of course share the structure for C1, but you need to create these nodes to merge them together, and that's where the blow-up is. So you'd like to have a representation that minimizes the size of that formula.
So it's like a multi-terminal bit ADD or something. Well, then, I mean, you want to be fast.
I'm sure there could be other representation that do it, but
you need the ADD because you need multiple outcomes. Yeah,
we could.
Yeah.
This worked conveniently. It's easily mergeable because often the operation that you do most is take 2 of these when they come to an if statement and need to merge them. So ordering them and merging them as a merge sort thing was useful. And we also get that sort of assertion efficiency for free, essentially. So there could be other representation, but perhaps the goals are the same as with BDD. How can you represent a formula in a compact way, right? And that's it.
So when defining a DSL on top of this infrastructure, how much do you have to understand about the underlying machinery, or to what extent do you find it useful to understand the underlying machinery to where maybe if you define the DSL too naively, it might have inefficiencies, for example? Or have you run into situations like that where you kind of have to massage the definition of the DSL?
You could run into inefficiencies, but what we try to do here is give people recipes so that they just start with something like this, where you have a grammar, an interpreter, and essentially copy that. And
so kind of as long as you follow the recipe.
That's the hope. That we want to standardize into a set of design patterns, not only because the good recipes is good to preserve, but also Grisette is easy to use if you know monads, and not the people who usually want to use this are those people who realize, oh, Z3 is really useful for what I need to do, but now I ran out of steam and the complexity of my system is too much to build constraints by hand. I want to generate them somehow. And at some point, Z3 pi is too low level. And at that point, you would like to write a DSL and generate these constraints. Those people usually don't speak Haskell and monads. So we are now even hiding that to a large extent so that there is an easy curve for people to start using it. So both for recipes on how to get good formulas and don't need to know much about monads.
Thanks.
Thank you.
Okay, if there are no more questions, let's actually stop on time. So let's thank Ras once again. Thank you, Ras. And now we have a tea break, which is